All right, let's just dive right into this. Take a quick look at the device you're using to watch this explainer right now. It probably fits right in the palm of your hand. Or, maybe it's resting easily on your lap. Now I want you to imagine a machine that weighs 30 tons, takes up 1,000 square feet, and literally requires an entire team of people just to operate it. It's kind of hard to believe those two things belong to the exact same family tree, right? Well, welcome to our explainer on the Great Shrink. Today, we're going to look at 80 years of computer history, and we're going to follow one of the absolutely most fascinating technological narrative arcs of all time, the incredible shrinking computer. So here's our roadmap for the Great Shrink. We'll start with the room-sized titans, move on to the transistor revolution, see how we brought power to the people, untether completely in the portable generation, and finally arrive at the ubiquitous computing era. Okay, part 1, the room-sized titans, stretching from the 1930s all the way to the 1950s. Now, picture this era. Computing back then required massive physical effort, huge cavernous rooms, incredible amounts of electricity, and just thousands upon thousands of glowing vacuum tubes. Born largely out of military necessity during World War II, machines like the 1944 Colossus codebreaker were built specifically to decrypt complex Nazi Lorenz ciphers, something that fundamentally altered the course of the war. Then, in 1946, the ENIAC was unveiled in the US. By 1948, over in the UK, the Manchester Baby actually ran the very first program on a digital electronic stored program computer. And by 1950, Britain's Pilot Ace managed to pack some pretty serious computing power into a relatively compact 12 square feet, and that was all based on ideas from computing pioneer Alan Turing. The sheer scale of these machines is honestly hard to even wrap your head around. The 1946 ENIAC alone weighed 30 tons, took up 1,000 square feet, and relied on 18,000 vacuum tubes. Programming it, well, that required physical panel-to-panel wiring and flipping manual switches. But here is the truly mind-blowing part. It was believed that the ENIAC did more calculating over the 10 years it was in operation than all of humanity had ever done prior to that time. Just try to compare that to the microscopic transistors inside the device you're holding right now. It's wild. Yet, as giant as these calculators were, visionaries were already looking ahead. In 1950, Edmund Berkeley prophetically wrote about his design for the Simon 1 relay logic machine. He said, "We shall now consider how we can design a very simple machine that will think." He actually wanted to build something small enough to fit inside a grocery store box. And that beautifully transitions our narrative from basic, giant calculators right into the radical concept of true personal thinking machines. Which brings us to part 2, the transistor revolution, covering the 1950s and 1960s. The invention of the transistor stepped in and literally changed everything. It replaced those hot, bulky, and super fragile vacuum tubes and completely reshaped the physical landscape of technology. Transistors made computers exponentially faster and so much more reliable. By 1956, MIT completed the TXO. Then, in 1964, IBM announced the System/360, which was a family of mainframes that really cemented IBM's dominance in the business world. That exact same year, the CDC 6600 supercomputer achieved unmatched speeds. And crucially, by 1968, the Apollo guidance computer debuted. Transistors enable this essential shrinking of technology, which, as we know, was absolutely vital for the space race. But hey, it wasn't all just dry mathematics inside these early programmable computers. Early programmers were incredibly creative. MIT's TX0, for example, hosted an early version of 3D tic-tac-toe. And brilliantly, it ran a program featuring a virtual mouse navigating a maze to find martinis, becoming increasingly inebriated as it went. I mean, it just goes to show that human playfulness has always been a driving force in computing, right from the start. 10,000. That is the jaw-dropping number of commands Apollo astronauts had to manually enter into the Apollo guidance computer for each trip between the Earth and the Moon. Engineers at MIT had miraculously shrunk a computer the size of 7 refrigerators down to a 70-pound box taking up less than a cubic foot of space, using some of the earliest integrated circuits. But to navigate it, humans still had to painstakingly punch in 10,000 manual commands. No pressure, right? Moving on to part 3, power to the people, spanning the 1970s and 1980s. If the transistor shrank the computer, well, the invention of the microprocessor completely democratized it. This is where we begin to see computing come out of the sterile laboratory and straight into the living room. In 1971, the Intel 4004 microprocessor arrived, packing massive power onto a single chip. By 1975, hobbyists were actually building the Altair 8800 from a kit. Just 2 years later, in 1977, we see the release of fully assembled systems like the Apple II and the Commodore PET. And by 1981, the IBM personal computer launches, gaining widespread adoption by industry and households alike. But while the personal computer was sneaking into the home, institutional computing was evolving too. Take the Cray 1 supercomputer, introduced in 1976. Used for massive tasks like nuclear simulation and weather forecasting, it had this highly unique, futuristic C shape. Why a C? Actually, it wasn't just for aesthetics. That C shape physically reduced the length of the internal wires, decreasing the time signals needed to travel across them, which drastically increased its speed. And each unit was so complex, it's like a giant puzzle that took a full year to assemble and test. $10 million. This era was really defined by this vast, incredible divide. On one hand, you had individuals buying an Apple II or a TRS-80 for under $1,000 to learn programming at home. And on the other, you had massive institutions spending $10 million a pop for state-of-the-art supercomputers like the Cray 1. All right, part 4, the portable generation, jumping into the 1990s to the 2000s. So we had gone from the room to the desk, and now we were untethering completely. Portability became the ultimate driving force of innovation. Over this decade, the form factor just kept shrinking. In 1991, Apple's PowerBook set the standard for modern laptop design with its built-in trackball and palm rests. By 1993, Apple tried to shrink things even further with the Newton Personal Digital Assistant. In 1995, IBM released the ThinkPad 701C laptop, and by 1996, the Palm Pilot arrived, popularizing the truly pocket-sized connected organizer that you could easily sync with your PC. I actually want to pause on the IBM ThinkPad 701C for a second, because it highlights this super fascinating engineering problem. As computers got smaller, human hands didn't. We still needed space to type. IBM's brilliant mechanical solution was the butterfly keyboard. When you open the laptop, this interlocking keyboard automatically expanded to be wider than the actual laptop case itself. It is such a beautiful example of hardware adapting to human ergonomics during the Great Shrink. And that brings us to our final era, Part 5, the ubiquitous computing era, spanning the 2010s to 2015. This is really the climax of our 80-year narrative. Computers didn't just shrink. They became so small and integrated that they seamlessly blended right into our everyday environments. In 2010, the iPad bridges the gap between phone and laptop. In 2011, the Nest Learning Thermostat brings the Internet of Things into our homes, actually allowing our climate control to learn our habits. By 2014, researchers developed the microscopic micromote. And in 2015, the Apple Watch puts immense computing power directly onto our wrists, complete with health and environmental sensors. Now, while consumer tech was shrinking down into our pockets and onto our wrists, institutional supercomputers were simultaneously achieving exponential leaps in processing speed. In 1997, ASC Red hit 1.3 teraflops. In 2002, the Japanese government built the $600 million Earth simulator for global climate models. And by 2009, IBM's Roadrunner completely shattered previous records. The IBM Roadrunner was the first supercomputer to achieve a sustained performance of 1 petaflop. Let that sink in for a second. That is 1,000 trillion floating point operations per second. It was used to analyze financial data, render real-time 3D medical images, and model complex global phenomena. The sheer scale of processing capability had become almost unfathomable at this point. To really tie this whole 80-year narrative arc together, just look at where we started versus where we ended up. In 1946, we had the 30-ton room-filling ENIAC. By 2014, the University of Michigan Micromote became the smallest computer in the world, measuring just over 1 single cubic millimeter. From 30 tons to a speck smaller than a grain of rice. Unbelievable. And this leads us to this absolutely amazing concept known as smart dust. These micromotes are so incredibly small and consume so little energy, literally a trillionth of a watt, powered by a tiny photocell, that they can be used as invisible sensors. Imagine an ecologist sprinkling thousands of these tiny microscopic computers from the air across a vast agricultural field. They instantly begin collecting and transmitting real-time data on soil moisture, air temperature, and sunlight. The computer has shrunk so much, it has literally become a part of the environment itself. Which leaves us with one final, pretty provocative question. Where does computing go next, now that it is smaller than a grain of sand? We've gone from machines that require an entire building to operate, down to smart dust that we can't even see with the naked eye.
The story of computing is one of relentless innovation, shrinking physical boundaries while vastly expanding human potential. So, as you look at the device in your hand today, just remember, you are holding the culmination of 80 years of brilliant engineering. Thanks so much for joining me on this explainer, and keep wondering what the invisible future of technology holds.